Deepika, are you in the meeting?
Yes, sir.
Start from the one. Start from the Shanti Swarup sir, shall we start, sir?
Yes, we'll start, sir. It already is 6:02.
Okay, sir. Deepika, you can formally introduce today's resource person.
Yes, sir. Good evening, everyone. On the behalf of Comrades College of Engineering and Technology, Department of Electrical and Electronics Engineering, I am honored to welcome you all to this faculty development program on navigating the green revolution, integrating electrical vehicles and hydrogen fuel technologies for sustainable mobility. Faculty development program is a platform dedicated to enhancing our teaching skills, research abilities, and academic leadership. In an ever-evolving educational landscape, continuous learning is essential, and this program offers valuable insights, innovative strategies, and opportunities for collaboration. First and foremost, I would like to extend a warm welcome to our esteemed guest speakers, faculty, facilitators, and participants. A warm welcome to our eminent resource person, Dr. K. Shanti Swarup, professor in the Department of Electrical Engineering at the Indian Institute of Technology, Madras, who has associated with this program to share his expertise with us. We are truly honored to have you with us and look forward to embrace this session. Let us engage, exchange ideas, and work together towards academic excellence, wishing you all productive and enriching experience ahead. The objective of the faculty development program is to enhance the teaching, research, and professional skills of educators, equipping them with modern techniques, technological advancements, and innovative strategies to improve student learning outcomes. Aims to foster a culture of continuous learning, collaboration, and academic excellence by providing a platform for faculty members to exchange ideas, explore best practices, and stay updated with the emerging trends in education and research. Ultimately, the program seeks to empower educators to become more effective mentors, leaders, and contributors to institutional growth. Before let's begin the session, I'm happy to introduce our resource person to this session, Professor K. Shanti Swarup. It's a distinguished faculty member in the Department of Electrical Engineering at the Indian Institute of Technology, Madras. He earned his PhD in Electrical Engineering from the Indian Institute of Science, Bangalore in 1990. Before joining IIT Madras, he held positioning as a visiting research scientist at Mitsubishi Electric Corporation in Osaka, Japan, and a visiting professor at Kitami Institute of Technology in Hokkaido, Japan. Between 1992 and 1999, since 2000, he has been a professor at IIT Madras. His research interests encompass computer modeling, simulation, and analysis of electrical power system, numerical optimization, digital and numerical protection, substation and distribution system automation, and energy management system, and SCADA. Throughout his career, Professor Swarup has made a significant contribution to the field, authoring numerous publications and guiding several doctoral theses. He has published 299 articles in reputed journals, and in conference proceeding under his guidance, 11 scholars are awarded with PhD degree. Energy management in e-vehicles and hydrogen fuel cell vehicles focus on optimizing power usage, efficiency, and sustainability. EVs rely on battery management system to regulate charging, discharging, and thermal control, while HFCVs use fuel cells controllers to manage hydrogen consumption and efficiency. Both technology utilize regenerative braking to recover energy and extend range. Advanced energy distribution system balance power between the battery, motor, and auxiliary components for optimal performance. Additionally, Integration with renewable energy sources enables sustainable charging for EVs and green hydrogen production for HFCVs, reducing environmental impact. Thank you, sir, for your association with this program. I am sure the session will provide us the valuable insights and enhance our teaching methodologies and research skills. We are privileged to have you with us today, and I'm confident that the session will be both enriching and inspiring. Now, I request the Professor K. Shanti Swarup to address the gathering.
Good evening, everyone, and thank you very much, Ms. Deepika.
Thank you, sir.
Can you please enable the share option? I want to share my PPT.
Sir, you can share, sir. It is already in enable, sir.
No, I'm not able to share. It was earlier active. Now it is. Is it visible now? No, is my presentation visible?
Yes, sir. Yes, sir. Visible, sir.
Yes, sir.
Sir, visible, sir.
Okay. I'll try to put it in full screen mode. Good evening, everyone. Okay. I'm just going to talk about. I'm sorry. 1 minute. I'm sorry. Just hold on. Is it visible? Presentation.
Yes, madam.
Hello.
Visible, sir.
Yes, sir. Visible.
Yeah, please. Good evening. I'm going to talk about energy management systems in electric vehicles and hydrogen fuel cell vehicles. I'll also show some of the work we've been doing. Okay. Thanks for this. Inviting me to give a lecture. Okay. I have time till 7:30. I'll try to finish early and I'll give some time for questions. Okay. This is introduction about me and my areas of research. Okay. This is where we work on energy management systems, mostly for automation, control, and protection. Now let's talk about energy management system. Initially, I'll spend some time, then I'll speed up so that you can understand. Energy management system that uses both software and hardware to monitor, control, and optimize energy use. It's mostly used in power grid, residential, industrial, commercial, and agricultural. It ensures availability and reliability of the power. Okay. Several programs are executed in energy management system. Most of them they do the task of estimation, assessment, identification, and contingency. There are different types of EMS. Mostly we use electrical power management system, which is my area. Okay. And there are many like industrial energy management system, building energy management, home energy management, and community energy management.
Swarup, sir, sorry to interrupt, sir. Sir, your slides are not in full screen mode, sir.
Now it is there.
It's not in full screen, sir.
Now it is in full screen.
No, sir. Sir, kindly press slideshow mode, sir, on the
Hello?
top. It's not in full screen, sir.
Now is it in full screen mode?
No, sir.
I'll do one thing. I'll share it with you. Can you please do that? So I'm using full screen mode only.
Sir, can you press slideshow, sir? There
Yeah,
is a main.
pressing,
That is
At the bottom, sir.
yeah, I'm pressing only that.
Okay, sir. You can proceed, sir. No issue, sir. We can able to see, sir. No issue. You can proceed, sir.
I'm seeing how to do that. Put in full screen mode only.
You can reduce the size, sir. You can zoom out and you can continue, sir. No issue, sir.
Could you please tell me if it is.
Now it is okay, sir. Now it is okay. You can continue with that, sir.
Okay. I'll be concentrating mostly on electrical vehicle energy management system. Mostly EMS consists of data collection, monitoring, reporting, and optimization. They also perform forecasting and prediction. In electric vehicle, all these three are widely used: data collection, monitoring through sensors, reporting, and optimization. Let us see electric vehicles. The typical electric vehicle is like this. It uses battery packs. I'll skip the introduction. This is how the components of an electric vehicle. I'm sure many of you they have seen this. And also they use regenerative braking. And mostly it consists of charging infrastructure, power electronics, and the motor. There are different types of electric motors used in EVs. Brushless motors, brushless DC, AC induction motors, etc. And when it comes to the battery pack, this is where the heart of an EV is. It uses lithium ion, nickel metal hydride batteries, nickel cadmium, lead acid, and etc. Now, these are the various types of electric vehicles. One is called battery electric vehicle, next is called plug-in hybrid electric vehicle, and hybrid electric vehicle. These all comes under different category. Some of them use gas as a fuel, some of them use gas and fuel, and some use only battery. Why I'm telling this is next when we go to fuel cell, you can see how the difference, how the fuel cell is used along with the battery electric vehicle. This is a typical charging infrastructure for electric vehicle. This is very, very important. There are different types of charging. Okay, low level, fast level, and rapid DC fast. At different voltage levels. Charging infrastructure is very, very important for electric vehicle. And mostly a major component is the power electronics component, which uses inverters, DC-DC converter, bidirectional DC converter, many more. Battery management system is a very, very important aspect of this electric vehicle. Now let us see what we meant by electric vehicle energy management. I call it as EVEMS. An electric vehicle energy management system provides significant benefit to the EV. It optimizes and stabilizes energy flow within a balanced grid while ensuring more reliable service and quality power. This is how a typical energy management in EVs looks like. It monitors, it controls, and optimizes the energy use. Okay? When I say optimizes, sometimes it minimizes, sometimes it maximizes. So it has a very important property, unlike any energy management system. The main aim of EV energy management is to improve the EV's range, battery life, and overall performance. This is a typical diagram of a charging station. A typical schematic, which you can see here, different EVs are charged.
Swaroop sir, sorry to interrupt, sir. Actually, currently we are viewing 9th slide, sir.
Oh God. Then I'll go to PowerPoint presentation. This is better. This is clear.
Now it is changing, sir. Now it
Yeah.
is showing 23rd.
Yeah, that's why I'll start with EVA. That's
Okay,
it.
okay,
This
sir.
is always
Okay, sir.
better.
Now it is changing, sir. Now it is changing. 21.
Because I kept in PowerPoint. Okay. Now
Okay,
I'll.
okay, sir. You can present in this mode itself, sir. No issue.
Yeah, that's why I was telling. Okay, we'll start with this. The electrical
Okay.
vehicle energy management system. It tries to optimize and stabilize the energy flow while ensuring reliable service and quality power. Typical schematic of energy management system is it monitors, controls, and optimizes energy usage. Monitors, controls, and optimizes. It has three performance indices, and it tries to improve the range of electric vehicles, the battery life, and overall performance. So it's like a multi-objective problem. If you see this EV is charged from different phases. Okay, the three phase. So EV1 is charged. This is a balance in charging of EVs. Okay. The advantage of energy management is to create a balanced distribution network, and also the most important thing is EVs share the information between electric vehicles and the charging infrastructure. Okay. They use 5G communication nowadays, and electric vehicles are having more advantage when it comes to sharing the charging infrastructure. For example, Ather electric vehicle, as you've seen, okay, it's widely used. It has a lot of IoT-based computation, which shows the remnant charge, etc. Usually, this smart energy management, okay, it has something smartness into this. It has a powerful optimization tool for balancing the load and EV charging infrastructure. Nowadays, we have some fixed charging price. In future, we'll have what is called a dynamic prices and dynamic grid and dynamic energy costs. So the charging infrastructure is completely dynamic in nature. With dynamic rates of charging, time of usage, etc. This is called a smart energy management. And this is the various features of electric vehicle energy management. There are many properties. The most important thing is the third one. The energy management system is nothing but a computer-based system that is mainly responsible for the optimization of charging and energy output of batteries, so that maximum operating range and improved performance can be achieved. And also to estimate the available range. Remember, I said this energy management is to estimate what is the range of the battery, the the distance of the vehicle, and how much the battery can retain its charge. This, this makes energy management of every vehicle a very challenging task. This is a typical diagram of EV energy management system. You can see here, most of them are bidirectional information. You have energy management, you have instrumentation, vehicle diagnostics, vehicle controls, motor control, battery. Everything is bidirectional. Information goes and it receives. So it is completely a closed loop type of control. This is a typical diagram of how energy management requires. You have demand response, energy management, efficient operations, how to adjust the load profile while charging electric vehicles. So this EMS collects, stores, and displays and analyzes the data. This is widely used in the present electric vehicle energy management system called as Ather. Another schematic of energy management in electric vehicle because we are doing some work along with Energy Consortium. So they gave me some slides and I'm presenting it on their behalf. We have electric charging and discharging, regenerative braking, and vehicle to grid interaction. EMS controller is very, very important. Nowadays they use AI and machine learning applications to understand the role of energy management and charging. This is how a typical, earlier I showed smart energy management, now I say intelligent energy management. Both of them are same, but this intelligent energy management performs many tasks. As you see here, it optimizes, it estimates, it predicts, it regulates, it directs, it adjusts, and it analyzes, and also identifies. So many 10 properties are there in an energy management system. All of them are linked. Okay? So 10 output of an energy management system for an electric vehicle. When you add navigation, for example, GPS to an intelligent energy management system, which is many EVs have, it can plan more efficient routes, it can locate EV charging stations, and it can modify the range predictions. Nowadays, many EVs have this also option. Okay, it can identify which is the nearest EV charging station, okay, based on how much remnant charge you have on the battery. Okay, now everyone has talked about electric vehicle. Now we'll talk about hydrogen fuel cell. Why it is gaining more importance? The hydrogen fuel cell vehicles are the vehicles of the future. Let us see a brief introduction. The typical hydrogen fuel electric vehicle is like this. It uses hydrogen to produce electricity, which powers an electric motor. These are similar to electric vehicles, but they do not rely on a battery to store energy. They store hydrogen in tanks and convert it to electricity. This is a typical diagram you can see here. The fuel cell in vehicle generate electricity by using oxygen from the air and compressed hydrogen. Mostly these HFCVs are called zero emission vehicles. Same like plug-in electric vehicles. The first modern fuel cell vehicle was modified Alice Chalmers farm tractor with a 15 kilowatt fuel cell. It is going more successful. And the various components in an HFCV. Assuming I don't want to go in detail. Similarly to that, you have a fuel cell stack, DC-DC converter, thermal system rating, etc. We'll see more in detail. This is a typical block diagram. I think this will be more clear to you. You have a fuel cell here. You have a DC-DC converter and DC-AC inverter, which drives a motor traction. And you have a battery charge discharge cycle. We have a DC-DC converter to decide upon the water circulating, fuel circulating, and air circulating. Why I am showing this diagram is in IIT Madras Chemical Engineering Department. We have not exactly a fuel cell vehicle, but a energy storage is called redox flow battery. It is similar to this. We have a water circulating pump, fuel circulating pump, etc. This gives the highest battery charging performance. This is how a typical hydrogen internal combustion engine works. Look at this chemical reaction. Hydrogen plus oxygen is equal to water plus heat. The steam that is produced pushes onto a piston. This enables the vehicle to move. You see the animation. 1, 2, 3, 4 stages of hydrogen internal combustion. And this is the working of a fuel cell vehicle. Okay. This has a battery, a fuel cell, a hydrogen tank, an electric vehicle, and a water. Water is the output of this fuel cell. Okay. This is the advantage of a fuel cell over electric vehicle. Let us see, this is the various stages of hydrogen energy storage. Okay. Before going into fuel cell, you need to know what is hydrogen energy storage. This plays a very important role. Nowadays, the government of India has set up several hydrogen energy storage plants. For example, Power Grid and Grid India has set up many hydrogen plants. And some of the problem, okay, if you try to formulate the hydrogen fuel cell vehicle, it tries to minimize the hydrogen consumption, it tries to maximize the efficiency, it has to extend the lifespan of fuel cell based on the driving demands and the real-time data. This is how a hydrogen fuel cell vehicle is characterized. Now, recent news you might have seen, the Indian Railways tested its first hydrogen fuel cell train between Jind and Sonipat section of Northern Railway. In fact, last month I've been to IIT Guwahati. They're doing a lot of work on hydrogen energy storage for electric vehicles. And the train is developed at the Integral Coach Factory in Chennai, Avadi. First of its kind. And what are the benefits of hydrogen fuel cell? Green transportation, sustainable. Hydrogen fuel trains can operate for more than 18 hours without refueling. It has low cost of operation. And hydrogen fuel cell achieves the target of net zero carbon emission goal. This is the most important property of hydrogen fuel cell. Okay, this is the main features of a fuel cell. Don't want to go into detail. Now suppose I compare a lithium-ion battery EV and a fuel cell electric vehicle. I'll keep this for some time. I want all of you to have a look at it. Can you judge which one is better and why? Each has its own advantages and disadvantages. Lithium-ion battery versus fuel cell. Fuel cell has a high upfront cost, so it's very expensive. But the cost is expected to come down with time. However, hydrogen fuel is less expensive. Okay? So there is a balance between investment cost and operation cost. That's why fuel cells are called the fuel cells of the electric transportation of the future. Now let us see how to integrate energy management system with HFCV. This is the main talk which I'm going to spend time about. Okay. Integration of EMS to hydrogen fuel cell. More than the operation of the fuel cell, you have many things more. You have what is called data analytics and real-time monitoring. This is where the information technology plays a very important role. Next is visualization and interpretation. Suppose I want to do energy management. This is a continuation of that work. Look at this diagram. Hydrogen fuel cell vehicle. We have a PEM fuel cell, DC-DC converter and a battery and a hydrogen tank. Again a DC-DC converter, PMSM driver and a PMSM. This is how a schematic is, and each one is shown here. This is the fuel cell, this is a different mode of detection, this is a rule-based EMS, and the dynamic power factor. This is what is very important, dynamic power factor EMS. This is how energy management of fuel cell plays a very important role. This is more clear in this diagram. Usually you have power distribution, fuel cell protection, the battery management and driving condition. Some of our students in our electrical department are working on battery management system of fuel cells. If you see the flow diagram, if you see here there are different levels of EMS. I'm talking about energy management system. First level is the working condition, where it is called vehicle state, whether it is idling or powering mode. what is the state of charge. In the next level, you have the power mode of the fuel cell and the electronic control rule base. In the second layer, you have the dynamic power production mode, that is acceleration. This is clear from this diagram. I spent some time on the diagram. Look at this diagram carefully. There are different operating states for the fuel cell. And energy management system has to balance all of this. You see here, on the left hand side, there are 4 states: idling state, acceleration, fixed speed cruise, and braking. In the idling state, only the 3 squares are on, one is off. That means it doesn't consume much of a power. So only 3 states are there, shown as a bracket. So the best performance is 3. In the acceleration, look here, the green level becomes 8 of them. Battery charging is blue, which is 4. Discharging becomes 3. When it is accelerating, the battery will discharge. And this fuel cell maximum power availability is 7. So what do you understand from this? It's like a matrix. Charging, discharging, fuel cell maximum power, and the best performance. This is during acceleration, during quick speed cruising, and during braking. So what do you understand from this? I leave it to the audience. I'll keep for some time. This is how an energy management system works. You have to balance between 4 modes of operation: best performance, battery charging, battery discharging, and FC, fuel cell maximum power. Suppose I want to optimize. I said optimization, estimation, prediction, many more. What do you try to optimize? What do you try to minimize? There are many things. Optimization can be minimization or maximization. In some cases it is minimization, in some cases it is maximization. So this is what makes energy management systems of hydrogen fuel cells more challenging. More than the drivetrain, it's mostly the how do you formulate the problem. Sometimes you have to accelerate, sometimes you have to save the battery, how much distance. So you have to it's a multi-objective optimization problem. We are looking at as an optimization problem, which I'll show you some of the studies which we are doing. And this is the drivetrain. Usually in fuel cell, this is what is a drivetrain. Look at this. This is what is called the future hybrid electric vehicle. It uses fuel cell, it uses lithium-ion and supercapacitor. All 3 are used. In fuel cell, use an unidirectional DC-DC converter. Power flow is only one way. Lithium-ion battery use a bidirectional converter for charging. Okay, AC-DC converter, and supercapacitor also is bidirectional. This is an improvement over both electric vehicle and fuel cell. They use a supercapacitor also along with this, which is what we call hybrid electric vehicle. Instead of fuel cell, along with fuel cell alone or battery alone, a combined property of all 3 potential properties is what is called the fuel cell of the future, hybrid electric vehicle. Now look at the advantages and disadvantages. Advantages: zero emission, high efficiency, sometimes frequent hydrogen refuels, long range. It goes up to 500 to 600 kilometers. And it doesn't depend upon battery, low dependence on battery. Disadvantage is a limited hydrogen fueling infrastructure. Unlike electric charging, you need to have hydrogen fueling infrastructure also. High production cost, that means investment cost, expensive fuel cell. And hydrogen is highly inflammable. So it should be very careful. And energy loss in production and transport leads to efficiency. Usually, energy loss in the production and transportation is a problem. It reduces the efficiency. future solution, we have solid state energy hydrogen storage. The hydrogen storage plays a very important role. More than the hydrogen electric vehicle, storage of hydrogen is what's gaining more important. The different types of hydrogen, green hydrogen, brown hydrogen, blue hydrogen, etc. We need to use hydrogen production from renewable energy sources, which is called as green hydrogen. And most of the research is going on fuel cells for cost reduction. Now, with this, I want to show some of the research work IIT Madras we are doing on electric vehicles. We have done this work on uncertainty handling of electric vehicle aggregator. That means EV chargers. So many of our students have worked on this. About 6 students developed this and we published in a conference. Okay, I show what we have done. This is how we did electric vehicle charging aggregator. This is nothing but an energy management system which we have done. It's about plug-in electric vehicles. How to coordinate between plug-in electric vehicles during charging is the main aim of this work. I did a lot of literature review because nowadays when it comes to electric vehicle charging, we have grid to vehicle and vehicle to grid. In our country, we only have grid to vehicle. In the future, we'll be having vehicle to grid. Of course, nowadays, some places have vehicle to grid, but there are a lot of limitations. Okay. In the future, in the not too near future, we'll have both grid to vehicle, vehicle to grid, and even vehicle to vehicle. All 3 options. So we studied these options earlier. This is a typical example we have taken. Okay. We've taken 2 identical electric vehicles charged in a parking station. It is called PE1 and PEV2. Usually at the time of arrival, the time for which they remain parked in the charging station and the battery energy on arrival is considered for both. We consider time of usage of pricing because TOU pricing is dynamic pricing. Okay? It's mostly used for charging of electric vehicles. We consider 2 scenarios. I just explained so they can understand. In the first scenario, PEV charges without any scheduling. There's no priority. Okay. In the second scenario, we try to charge them with priority for vehicle to grid operation. Okay. This is the cases, 2 cases we have taken. Okay. For example, you see here 2 time slots. This is the battery status. This is the cost. Okay. Electric vehicle 1 and electric vehicle 2. If you see the description is given here. One electric vehicle arrives at time T1 with 60% charge remaining and stays in the parking slot till T2 and PEV2 arrives at T1 okay, with 40% charge. This is how we calculated this for scenario 1 and the total cost for charging both PE1 and PEV2 is 110 plus 110 is 220 rupees or currency whatever. In the scenario 2, we try to do V2G also. Here everything is G2V, grid to vehicle, grid to vehicle. We are charging. Suppose we take V2G, vehicle to grid option. Okay. This PE1 has vehicle to grid option, where the PEV2 has no vehicle to grid. This option is available based on how you charge the electric vehicle. So in this, we developed an energy management system where okay, we showed that by this scenario, we can have a reduction in, we can get the cost of 90 and this is 110. By using grid, vehicle to grid, okay, you can have a savings of 20 current, I'll say units of currency, either rupees or dollars or whatever. We try to show how an electric vehicle with V2G facility can have a lot of savings with variable price. And as an example, we have taken for 5 electric vehicles N1 to N5. We have taken 8 time slots of 3 hours each, so 8 into 3, 24 hours. For each time slot, all vehicles are getting charged. Second hour, all vehicles are charged. The third hour, only few vehicles are getting charged. Others are completely charged. Only 3 are vehicle are charged. In the fourth hour, only 2. Fifth and sixth, there are no charge. Again at 8 hour, this vehicle again comes here for charging. This is how the scenario we have considered. And the limits of the battery are 13.5 kilowatt and 6 kilowatt. This is how we created a scenario for charging of electric vehicles. Different thing. Initially they charge. After them, there's no load on the electric charging infrastructure. Again, after some time, they come here. They come for charging. Once the battery becomes low, like that we consider different scenarios, and we got good results to showing that. Okay, we use what is called an information gap decision theory to determine if we use vehicle to grid, we can have a lot of profit per year. Okay, and we showed it how this can be done. And we use, when we said optimization, we use what is called a nonlinear NLP problem and converted it to a mixed integer linear program. Mostly, as I said, the charging of electric vehicle management system is mostly an optimization problem. More than charging, you have to optimize several parameters. The charge, the distance, the price. This is what makes EV EMS a very challenging problem. Some of the references. And we are doing some work with Energy Consortium of IIT Madras. Okay. Some of our research students have done this work. I'll share it with you. They have done some work on energy management in electric vehicles. Because we have a battery center at IIT Madras. Okay. We have a EV charging. If you see, if you have come to IIT Madras, most of them are battery electric vehicles. The main buses are battery electric vehicles. We have a charging station here. Many two-wheelers are there. Four-wheelers are not there much, but most of the public transport is electric vehicle. So IIT Madras is using this public transport electric vehicle so that it wants to showcase to the city, Chennai and Tamil Nadu and other parts of the country, that it is possible to use electric vehicles. It reduces the demand for, they're trying to keep away petrol for internal combustion engine vehicles. A lot of study is going on in this. So some of the work done here is like this. The main aim, this was done by one of our colleagues. Okay. You have to maximize the range, reduce the cost, energy consumption, and minimizing the impact. That means you have to reduce the carbon footprint. These are main properties of using electric vehicles. And what are the key challenges in EV energy management? Battery degradation is one. Usually battery degrades. Okay. Thermal management. Okay. Heat generated during charging and discharging impacts the battery efficiency and lifespan. This is the most common problem. Once the heat generates, the vehicle comes to a stop. I'll give an example. Earlier, IIT Madras used to have a BHEL electric vehicle. Whenever people used to exceed more than the limit, the vehicle used to stop halfway. We had 4 such vehicles. All of them have been replaced. It was in 2005. We have a BHEL electric vehicles started. They were not efficient. If many people go on to that percentage bus, it used to get heated and it used to stop midway. Now the problem is solved. We have a huge capacity electric vehicle supplied by Ashok Leyland. It's called Switch. Now it can handle many people. And many more buses are flying from one part of the campus to another. Grid integration. This is still, we are only using grid to vehicle. We have not used vehicle to grid. Okay, this is what makes it more challenging. Battery degradation is a very important thing. Okay, we can't afford to charge every time the bus comes to a stop. During peak hours, the bus has to make many rounds. Okay, this is one of the key challenges in electric vehicle energy management. Look at the energy flow. One is called the storage, one is called the conversion, one is called the utilization. Usually energy is stored in lithium-ion batteries, LFP or LiNMC. Conversion, DC battery to AC motors, and utilization. Electric motor drive the wheels, regenerative braking, recovers kinetic energy. This is energy storage battery technologies. Remember I said IT Madras has the battery storage technology, they have a center. They are developing batteries for electric vehicles. These are the various properties of batteries. Lithium ion, they have high energy density, about 250 watt hours per kg. Only drawback is it degrades faster at high temperatures. LFP, thermal stability, longer lifespan, but it has a lower energy density. It can go up to long distance. And solid state batteries, highly safer, faster charging, but very high production cost. So nowadays, our country, most of the material science people are going towards solid state battery technology. They want to replace lithium ion with solid state and slowly reduce the production cost. When you say lithium ion, we are dependent on Chinese suppliers. They're the most bulk suppliers of lithium ion batteries. Okay. Now we want to be independent, so everyone is trying to go for solid state. Most of the ITs are developing material technologies for batteries. Okay, this is where the challenge lies nowadays. If you have a very good battery, then the EV will become a realization, or else it still remains a dream. Next is energy conversion and utilization. Mostly power electronic converters are widely used, as I mentioned. The inverters convert DC battery power to AC for motors, achieving as well as 97 to 99% efficiency. Okay. Power electronics are highly efficient, whereas the electric motors only around 95% efficiency. They use permanent magnet motors, which achieve about 95% efficiency. Okay. While optimized drivetrains reduce energy loss. So the three things: power electronics, which use converters, have 99% efficiency. Permanent magnet motors, around 95% efficiency. And optimized drivetrains is which is gaining more importance. They try to reduce energy loss in transmission, mostly in mechanical power losses, braking losses. All this constitute to energy losses. You can minimize the drivetrain losses, then the electric vehicle efficiency will be very high. And thermal management, as I was mentioning, is the most important problem in electric vehicles. You need what is called a cooling and heating systems. Okay. Liquid cooling maintains battery temperatures at about 20 to 40 degrees, while phase change materials, you might have heard about phase change materials, they absorb the heat during peak loads. As I mentioned, in our chemical engineering department of IT Madras, they are using phase change materials for electric vehicles for providing cooling facilities to electric vehicles. Temperature impact. High temperature accelerate degradation, while cold temperature increase internal resistance, reducing the range. So the temperature has to be maintained optimum. It should be maintained at optimal level. This is what is called continuous optimum. You need a continuous control between the minimum and maximum. Okay. You have to optimize the temperature in an electric vehicle. This is the challenge for thermal management in electric vehicles. And finally, as I said, smart energy management system. It's nothing but called the battery management system. This is where Department of Electrical Engineering, IIT Madras, Engineering Design, IIT Madras. Many departments are working to develop a smart energy management. This is what is called battery energy management. This monitors the state of charge, state of health, and cell balancing, preventing thermal runaway. Okay? You have to increase the life of the battery, so you can't allow it to increase the temperature. Okay, you have to maintain the temperature at a very constant value, certain range. State of charge, state of health, and cell balancing is done. We can't afford any cell to get damaged because it requires replacement. Replacing the batteries is still a challenge. In order to avoid replacing the battery, you have to optimize the temperature, state of charge, state of health, and cell balance, so that all cells are properly functioning without any of them getting damaged. And this is the charging strategies of bidirectional power flow. Most of you might have known this, but I'll explain this. We have a slow charging, which is AC. The power is about 3 to 22 kilowatts. The charging time takes about 4 to 8 hours, about 80%. Usually the use case is at the overnight home charging. Overnight home charge. You plug in the vehicle at the night. Okay, it takes about 4 to 8 hours. There's an intelligent charging which tries to see without drawing more current, more reduce. It tries to optimize between the current drawn and maintain the voltage profile. Because in the night time, many consumers use their appliances. Okay, till about 9 to 10. Only in the early morning, early hours from 12 midnight to 4 a.m. this home charging is programmed to. The fast DC, they take about 50 to 150 kilowatts. It takes about 30 to 60 minutes for charging. This is widely used in public charging stations. And ultra fast DC, it takes about 150 to 350 kilowatts. It takes about 15 to 20 minutes, mostly in highway corridors. So these are the various types of charging. Okay, and accordingly, the price is dynamic pricing is used here. It's called dynamic power pricing for charging of EVs. Suppose you have very little charge, you have to go for ultra high. You have very little charge on your EV, you have to go for ultra fast charge, and you have to pay more. So your EV will have a option to decide which charging it should go. It will also inform you which charging station you should go. This is widely being used. For example, Ather electric vehicle. I have seen one of my colleagues has. It has all these options. It will tell you how much remnant charge is there, which is the nearest charging station, and how much carbon emissions you have saved. And the future trends in EV energy management are this: battery technology advances. For example, solid state batteries offer twice the energy density and 10-minute charging, while solid sodium ion batteries provides a low cost alternative. So there's a trade-off between solid state batteries and the lithium ion batteries. Next is AI driven optimization. Remember, I said electric vehicle energy management is nothing but optimization, multi criteria, multi decision making optimization. This is where AI tools are gaining more importance. For example, neural networks are used to optimize the torque distribution, cutting energy losses by 20%, and digital twins simulate the battery aging for proactive replacement. Nowadays, most of the research by students and faculty alike are trying to use AI for optimization in electric vehicles. In fact, few of our students are using digital twins and cyber physical systems for electric vehicles to balance between energy, state of charge, state of health, range, etc. Finally, it's called sustainable ecosystems. EV act as a grid scale storage. It's called mobile. Electric vehicles are also called as mobile energy storage. Instead of fixed energy storage like fuel cells or other energy storage, EV acts as a mobile storage. Okay, so it is used mostly for demand response applications. They're also used as prosumers. For example, renewable energy, you have prosumers. So EVs find a very important role in this. EV act as a grid scale storage, integrating wind and solar energy, V2X networks. When I say V2X, X can be anything. It can be vehicle, it can be grid, it can be home. There are many things. They're called V2X networks, enabling decentralized energy trading, decentralized and distributed energy trading. Nowadays, electric vehicle charge is nothing but V2X. X can be grid, X can be home, X can be vehicle, and many more. Finally, this is the last aspect which I am showing. It's on strain on the grid from electric vehicle. This was the study our team had presented. This was done by Energy Consortium of IIT Madras. See, when you draw more power from the grid, what will happen? No one has considered this. So this study was presented by some of this group. It was presented at Melbourne Energy Summit 2024. Okay. Strain on the grid from electric vehicles and the opportunities within. This work was done in collaboration with Deakin University. Okay. And Dr. Nikhil Tambe is the COE of IIT Madras Energy Consortium, and Mohammad Firoz MK is an engineer. He is doing research along with me and Nikhil Tambe, Energy Consortium. Strain on the grid from EVs and opportunities within. Okay. This is the title. If you see the current grid status, okay, here I'll go slow. This is where the scope for work is. Look at the peak power in the grid. India's power grid reached a record-breaking peak demand of 250 gigawatts on May 30th, 2024. Reached 250 gigawatts, which corresponds to an annual growth rate of 6.5%. Okay. During May 2023 to May 24, electricity demand increased by 28.8 gigawatts. Okay. From 221.37 to 250.2 gigawatts. It shows an annual growth rate of 13%. So every year it is expected to increase by 13% or 15%. It can even go up to 20%. Okay. So demand has exceeded 20%. And suppose we use EVs for charging, again it will increase. So how are you going to support the grid? Is it through renewable energy? Is it through energy storage? You might have seen recently in the budget, our Prime Minister said he has sanctioned nuclear power plants. Because of this, several nuclear power plants have been started to support the grid. And this is a counter strategy. There is an Indian Energy Climate Center which outlines the need for battery electric storage system. As early as 2027 to significant evening power shortages. By 2027, they wanted to have battery energy storage. Which type of battery is still a challenge? Now the government is raising lithium-ion batteries. Nowadays, hydrogen energy storage battery. We have redox flow batteries. All of them are gaining importance. This is how it is. Demand growth at 6%, you need 4 gigawatts. Storage requirement. Demand growth by 7.25, 16 gigawatts. And the demand growth at 10%, you need 32 gigawatts to 140 gigawatt hours. 32 gigawatts and 140 gigawatt hours. Where do we get this energy? For example, the Central Electricity Authority of India has projected a provision for a requirement of 208 gigawatt hours from battery energy storage systems by 2030 to meet the rising electricity demand. Remember, 2030 is a deadline the Prime Minister has given that all vehicles should be electric in nature. By 2030, he says he wants to remove all internal combustion fuel vehicles. Even our Minister Nitin Gadkari also is saying by 2030 all vehicles should be electric vehicles. So imagine the demand and strain on the grid. It's very easy to mention that. How we're going to support this demand? So nuclear power is the only option available. That's why in the near budget, the Prime Minister said several nuclear power plants are going to start. Okay. Renewable energy has taken a back seat. Because we've been seeing renewable energy coming, but it doesn't have a good impact compared to nuclear energy. You see, the Tamil Nadu State Electricity Distribution Company is very much bullish about meeting demand with some smart planning. Okay. It has invested in pump storage and also floated a state policy. I should not say this, but it is still not taking the seriousness of the demand growth. You need smart planning. You can't say I'll use renewable energy alone. For example, Tamil Nadu uses what is called a green corridor. We have a lot of wind energy at Katihar plant power, but that alone is not sufficient. You need a good transmission network. Green energy corridor is there. That alone does not help. So you need to have energy storage, and pumped hydro storage is very little, 10 to 15% or more, not more than that. But where do you get the energy? Suppose you get wind energy, you need to store that energy. The redox flow batteries like Sumitomo Electric has started this. If you see here in the world, Sumitomo Electric from Japan has developed a 50 gigawatt redox flow batteries. It is there in Hokkaido. In fact, I was fortunate, I was in Hokkaido Electric Power Company. I went in with it's a very big redox flow battery. It can store up to 50 gigawatts of energy. Okay. Now, if we don't have any choice, we may have to buy that energy storage from other companies. Indonesia is making, Japan is making, Thailand, all of them are making energy storage devices except our country. We have to look at it, the energy storage requirement. And look at this current EV fleet status. If you want to see how much is the electric vehicle growth, as I was mentioning, EV buses are very less. Only two-wheelers, three-wheelers and four-wheelers are dominating. But EV buses are still low. We need more EV buses. Remember, our Chief Minister was telling he wants to replace all Tamil Nadu transport with electric vehicle buses. Very good thing. In the near future, we need to have. This will reduce the reduction. It's not just saying you should also have some numbers. So this slide shows the numbers which our energy consortium team has done. Okay. They got this data from the Society of Manufacturing of Electric Vehicle SME. Based on the data from the past 5 years, total battery sales of electric vehicles have reached 27 gigawatt hours, with nearly half or 44% occurring in the last 12 months. Mostly battery sales have surged from an average of 93 megawatt hours to 1,258 megawatt hours. A growth of approximately 1,250%. Look at the battery sales and the demand for energy storage. So if we don't have energy storage devices, we have to depend on other countries to supply us. We don't have inbuilt battery energy storage. We only want to use electric vehicle, but we are not thinking about the battery storage. So IIT Madras has a battery energy center which is developing some indigenous battery energy storage. It is developing some battery cells for electric vehicles. They are still being used inside the campus. They are not commercialized, but there's a lot of good potential to supply electric vehicle batteries. And EV battery projections. When you talk about electric vehicles, the most important thing is the battery. You see here, by 2028, market penetration battery will be like this. It's about by January 2028, electric vehicles. You can see here the battery energy, how much energy is required. This is a base case 12%, nominal case 23%. Bull means an approximate, and bull 2 and bull 1 are what is called as the rough category of estimating how much demand will be there. So India by 2030, the automotive industry that is fifth largest in the world is slated to become the third largest. 80% of two-wheelers and three-wheelers, 30 to 70% of cars and 40% of buses are projected to be EVs. Most of them are two-wheelers and three-wheelers. Mostly the buses are about 40% to be EVs. Okay. This is data obtained from NITI Aayog, and IIT Madras has done its own study. Okay. The normal case growth scenario itself went to 220 gigawatt hours of on-road battery capacity. This is how you need 220 gigawatts of battery energy by 2030. Where do we get this from? This is the challenge which is facing the Indian power grid. Okay, we have three things. NITI Aayog also is doing this study. Our IIT Madras has done its own energy consortium has done a study and said we need about 220 gigawatts of energy storage on the battery, on the road. That means we need mobile battery, total mobile battery of 220 gigawatt hours. How are we going to meet? Not just electric vehicles, but the battery management and production of battery cells is the challenge. This is what we have shown EV battery projections. Cumulative gigawatt by 2027. Base case, normal case. The bull case is what is called a rough case, what we can show. The growth at 12%, 23, 60 and 100%. By 2030, we need about 670 gigawatts of energy storage. The normal case is 220 gigawatts, but if you want to take a rough prediction, it's about 3 times 220 into 3, 660 or 660. This is the worst case scenario. We need about 660 gigawatts of battery energy storage or mobile battery. Where do we get this from? This is more challenging than the electric vehicles. And EV as a solution. Leveraging EV batteries. Cars will constitute 36% of the available battery capacity by 2030. Cars will consume about 80 gigawatt hour. Even a modest assumption of only 20% of that being available for charging, it consumes about 16 gigawatt hour. Cars will consume about 36, two-wheelers about 24, and three-wheelers about 39%. Battery contribution from each sector, cumulative, normal, and base case. This is how the anticipated energy consumption by 2030. We have not added buses. When the buses come, the demand will be even more. So how are we prepared for this? So this requires a lot of planning. More than the use of electric vehicles, how much do we have the battery capacity to supply electric vehicles? EV as a solution. One of them is called distributed storage potential for India. This work was studied by Energy Consortium. I keep repeating the term. Okay. There are many confluence of factors. Employees favoring put up charges on their own premises to counter employees to switch to EVs. Many residential apartments have EV charging. And the distribution companies favoring users of EV charging during daytime with solar. They want EVs to charge during daytime than in the night. Even though we prefer night charging at residential distribution companies, they want EV charging during daytime with solar. They don't want EVs to be charged in the night where there are evening loads. Not night load. Evening load starts from about 6 to 7 p.m. to about 12 in the midnight. So you can't use EV charging during the time, which is more preferable for consumers. Rooftop solar schemes targeting about 20 million homes. The Central Electricity Regulation Commission, they are trying to come up with dynamic pricing models. This is what we are working on. I'm working with Energy Consortium on dynamic pricing electricity markets, and they're trying to use it for charging of electric vehicles. Now, this is a perfect time for policymakers to think ahead. This is what it is. Energy policy plays a very important role for electric vehicles. More than making electric vehicles, how are you going to prepare yourself for the future? Some of the conclusions are EV fleet in India has already reached 27 gigawatt hours of total battery capacity and will reach by 2020 gigawatts by 2030 within normal growth projections. Okay. That means that 6% of that is anticipated to be cars, each with average capacity of 36 kilowatt hours. When I'm showing these conclusions, I want all of you to note that conclusions should be quantitative. We should have some numbers. It should not be qualitative. Whenever you make a presentation, okay, you should mention numbers. How much of energy, how much is the rear, how much is the percentage, how much is an annual capacity. This is what we call it as a very good conclusions. You should give some numbers, correct numbers. Okay. Those which are obtained from survey, okay, Central Electricity Authority, they all have websites. This study has taken 2 years to come to this conclusion. Not an easy task. The study 2 years, most of our PhD students supported that. Okay. It's taken 2 years to arrive at these conclusions. For example, Central Electricity Authority of India has projected and provision for a requirement of about 208 gigawatt hours from battery energy storage by 2030. This to meet the rising electricity demand in India. Battery energy storage is very expensive. Okay. And about 16 million houses, assuming average consumption of 10 kilowatt per household, would benefit even if just a fifth percentage of the EV cars were purpose for charging home. Repurpose for charging home. That means it is vehicle to house. Understand? This is where we use vehicle to X. Remember, I said instead of vehicle to grid, if you can charge from vehicle to house, it's called V2H. Okay, this will reduce the peak demand. Okay. This will empower individual house owners and residential complexes. Market is priming up to inducing a revolutionary electricity distribution and pricing models in an increasingly renewable energy rich India. This is the final conclusion. Renewable energy plays a very important role. Okay, for example, green hydrogen is nothing but hydrogen produced using renewable energy. This is where the future lies. We have to use renewable energy. It takes a lot of time. So in the meantime, we are getting nuclear power plants to provide us the energy requirement. By the time we will try to have our own hydrogen energy storage, battery energy storage, etc. Thank you. This is Energy Consortium work of IIT Madras. I would like to thank them for sharing the slides with this faculty development program. We want to share what IIT Madras is doing and how each of the faculty, students, research scholars, everyone should benefit. This just is but an awareness talk. It's not about electric vehicles and hydrogen fuel, but how much energy demand is there, energy predictions, are we prepared for the future? By 2030, very easy to say we want to replace all two-wheelers with electric vehicles or three-wheelers, four-wheelers. But are we prepared? Is the grid ready for such a rapid change? With this I'll stop. Any questions I want you to ask? I stopped at 19. I still have about 5 minutes for questions. Because there's another presentation at 17:30. I want to stop in time. Any questions? Feel free to ask. If I cannot answer, I'll say I cannot. But this is where the lot of future is there in electric vehicles. We have many students working on electric vehicles. More than the development, more than energy management, charging infrastructure, it's not just making a EV charger. EV charger also is important from a power system perspective. How do you balance all, optimize, predict, assess, estimate, identify all these things? They become a reality in electric vehicle. The electric vehicle is like something like a boon for our electric power people, where they can see all IoT, IT, everything can be visualized in an electric vehicle. You have charging, you have GPS, etc.
Thank you, sir. Surup, sir. Thank you. Any questions from participants?
If there are no questions, please send us an email to the HOD. Okay, he will send the questions to me and I'll try to answer. But I just want to add, this is a very interesting and challenging area for students, research scholars, faculty alike. Many students are doing innovative, they're coming up with innovative ideas. This is what I would like to say. Faculty or the research scholars, please take this up as a challenge. Energy management in electric vehicles and hydrogen fuel cell. This lot of challenge exists. Thank you very much.
Sir, Vidun, are you in meeting? Vidun?
Yes, sir.
Sir, 1 minute, sir.
Thank
Yes,
you
yes.
for your.
Midun, you can formally conclude.
Okay, sir. Thank you for your words, sir.
Thank you.
Thank you for the thought-provoking concepts on energy management in electric vehicles and hydrogen fuel cell vehicles, which aim to optimize energy efficiency, extending range, and enhancing performances. In EVs, it incorporates smart battery charging, regenerative braking, thermal management, and efficient power distribution to reduce energy losses. In hydrogen fuel cell vehicles, energy management includes optimizing hydrogen consumption, fuel cell efficiency, hybridization with batteries, and waste heat utilization. Both technologies aim to improve vehicle efficiency through advanced control systems, predictive energy strategies, and intelligent power management, ensuring sustainable and cost-effective transportation solution. I extend my heartfelt gratitude for the successful completion of session 9 in this faculty development program. A special thanks to our eminent speaker for sharing his invaluable knowledge and insights, enriching our learning experiences. Once again, thank you, sir.
Thank you very much.
Thank you, Surup, sir. Thank you, sir. Thank you very much, sir.
Thank you, sir. I'll take leave.
Thank you so much, sir. Thank you, sir.
Thank you.